We are solving a problem here. The problem is like this. Two materials of same thermal conductivity and dimensions. First, let's start there and see what's the meaning of that. Having same thermal conductivity means their K1 equal to K2. Having same dimensions means their lengths are same. Their areas are also same. Areas of cross sections are also same. They pass a heat of 2 joules per second when connected in series. Let's understand the meaning of this part of the problem. What it here says is, there is a material 1. There is another material of the same material and the same dimensions. They are at different temperature, so they pass heat. The definition of the heat, rate of flow of heat, is coefficient of thermal conductivity into A into delta theta by L, which can be rewritten as delta theta by L by Ka. L by Ka is also called as thermal resistance. So, this is having a resistance R. This is also having a resistance R because their lengths are same, their Ks are same, their areas are same. And these two are connected in series. As I have told you, as I have proved you in the earlier case, or I can prove that quickly. What happens in series is, the dq is going to be the same in series, that is dq by dt of the first case equal to the dq by dt of the second case, but the temperature differences are not same. Temperature from first to last, theta 1 minus theta 3, is temperature difference across the first one, that is theta 1 minus theta 2, plus temperature difference across the last one, theta 1 minus theta 3. As I told you, dq by dt equal to delta theta by r. So delta theta equal to dq by dt into r. Now delta theta is dq by dt, r of the combination, I can call it like r series. In the first case, dq by dt of r1. In the second case, dq by dt of r2. As I told you, in series, dq by dt is same, that can be cancelled. That implies r series equal to r1 plus r2. In our case, r plus r, that is equal to 2r. That implies dq by dt is delta theta divided by r. So we can write that as 2 joules per second. That's what is given for you. But in the place of the R, I have to write the effective resistance because there is a combination in series. So I have to write 2R. This is all happened when it is connected in series. Now let us write what happens when connected in parallel. When connected in parallel. Yeah. This is one rod. This is another identical rod connected in parallel. When you give a dq by dt, that is shared across these two. So the total dq by dt of the parallel combination is dq by dt of the first case and dq by dt of the second case when this is 1 and 2. But be careful, both the ends will have same temperature. Thus, we have noticed this clearly. In series, rate of flow is same, but delta theta is shared. Whereas in parallel, delta theta is same, dq by dt is shared. That's the difference between series and parallel. So dq by dt, we have a formula already. dq by dt can be written like delta theta by r. Therefore, what I can write? dq by dt means delta theta by r parallel equal to delta theta by r1 delta theta by R2. As I told you, delta theta is same in parallel, that can be cancelled. 1 by R parallel equal to, as the rods are identical, the resistances are same. So 1 by R parallel equal to 2 by R. That implies R parallel equal to R by 2. Be careful. In series, R series is 2R, but R parallel equal to R by 2. Then, what is rate of fluid flow is this question. dq by dt in parallel is equal to delta theta by R parallel has to be written. But R parallel equal to R by 2. What I got is delta theta by 2R equal to 2. From this, delta theta by R can be written by taking 2 to other side as 4 joules per second. So this is 2 into delta theta by R. That delta theta by R from the previous case is 4. So its value is 8 joules per second. So in series, under the same conditions, if there is a flow of heat of 2 joules per second, in parallel there is a flow of 8 joules per second. It is simply because in series resistance is more, in parallel resistance is less, thermal resistance is less. That's how we have to solve the problem. So if you notice, while solving the problem, I have not only solved a problem, but I have also explained and derived equations for effective resistance, thermal resistance when they are connected in series, and effective thermal resistance when they are connected in parallel. And we have also noticed one important point that in series, rate of heat flow is same, but temperature is shared, whereas in parallel, temperature is same, but heat flow is shared. That's it. Thank you for watching.